Good afternoon, this is Schweitzer, and this is one of our first discussions, well, maybe not our first one, maybe our second one, on atomic and electronic models. So this is going to start bringing in a lot of old information, and it's not assumed that, it is assumed that you've kind of know some of this already, so not that we can't backtrack and recatch some things, but this is just some information on the atomic and electronic models. So for example, we have the hydrogen atom. Now the hydrogen atom has one valence electron, so it would look like this: a proton in the center here, divided, and then around the outside here we have just one electron. Its electron configuration would be 1s1, and if you draw a Lewis dot, it would just be like so. Alright, then we got ourselves, let's say, helium. Helium has two protons, 1, 2 in the nucleus, has two electrons. They're both in the same energy level, so there we go. It would be 1s2 electron configuration. Helium would look like this. 1 and let's say 2. Okay. Alright, so now that energy level is full, so we're going to jump down a little bit lower here and just draw below here. So lithium also has one valence electron. I'm going to just draw it like that. Very similar to that of hydrogen, but it now has three electrons total. Three protons for neutral lithium would be 1, 2, 3, so three things in the center, and then we have in a first energy level, and then 1, 2 electrons, and then we have another energy level now coming because that one's full, and we have another electron here. Sometimes you might see it drawn as an E, or maybe just a dash, and this is sort of maybe we consider the Bohr model of an atom, and it's going to start running in some problems relatively soon if it hasn't already. Being three electrons, its electron configuration would be simply 1s2 and then 2s1. Quite often I would flip an electron configuration to an orbital diagram, and the way I would do that, and there are many ways, just one of them is to draw the suborbitals below and arrow up, arrow down, and this guy has just an arrow up. Of course, we'd want to note that an s orbital has two electrons max, therefore one suborbital, so every suborbital can hold two electrons. The p orbital can hold 6 electrons maximum for 3 suborbitals, and then the d would have 10 suborbitals, 10 electrons with 5 suborbitals, and then an F would be 14 electrons maximum with a total of 7 suborbitals. And I draw my electron configurations. Just keep in mind that I'm sort of mimicking my Aufbau chart, which would be 1, 2, 3, 4, 5, and continue. S orbital, p orbital, d orbital, f orbital, 1s2. That would be the helium. And then we have the second energy level, s orbital, can hold a maximum of 2. So, and then there's a 2p here, 6. And again, this video is not sort of solely on that. It's a little bit of everything. But that's where I'm mimicking as far as my electron configuration is concerned. Alright, let's add another proton and another electron. Okay, so I have my center nucleus with 4 protons. First energy level is full. Second energy level, okay. Now, this guy, a lot of times you might see them cluster them together like so for beryllium. And that is because when you drew the electron configuration, you'll note that they are in the same suborbitals. You might see that like that. 1s2, 2s2. If I convert this to an orbital diagram, you'll see the actual electrons in the suborbitals. Note that arrow up, arrow down does not matter as long as they are opposite spins. All right, let's add another proton and another electron. I'm going to give myself a little bit of room here. And this is going to be boron. And 5 protons in the nucleus. And we have, there we go, 1, 2, 1, 2. That's the beryllium. Add 1 more right here for 5 total, and then 3 valence. So it's going to be 1s2, 2s2, 2p1. So this is now in its own suborbital. Bring it up here. The p orbital has 3 suborbitals, and I might draw them all just to show that. And any box is fine. Up is down is no matter. Just pick one. We have carbon, which has 6 protons in the center. Then we have, moving along faster here, full, 1, 2, 1, and 1. So 2 separate. This is how they might show carbon atom. And I'll just backtrack 1 second for the Lewis structures. This is going to be 2 valence electrons. This is 1, 2, 3, and then 1, 2, 3, 4. Now again, as chemistry goes along, you find more and more things out, and you note that this guy usually bonds 3 times, so they might draw this thing separate like that. And carbon bonds 4 times, so they might show it like that. For my Lewis dot structure. Either way, 4 valence. So 1, 2, 3, 4. 1s2, 2s2, 2p2. And if I convert this to the orbital diagram, it would look like so. Arrow up, arrow down, arrow up, arrow down, and then 2 separate ones here. Keeping it simple. Alright, and then we have the next one is going to be nitrogen, which is going to have 7 valence, 7, and then I am not going to show all of the model. I guess we could just show them here. 7 protons, make it a little smaller, and there we go, and 1 more outer edge here. So this one's full, 1, 2, 3, 4, 4, 5, and I'm going to delete one of these guys. And show here and here. So 1, 2, 3, 4, 5 valence electrons. So 1, 2, 3, 4, 5. That's going to be 1s2, 2s2, 2p2, 3, and arrow up, arrow down, arrow up, arrow down, and then arrow, and we're all separating here. This separation here, where electrons do not match up with each other, they spread out first, is a good example of Hund's rule. You could read in a book, the definition of Hund's rule would state that the electrons matched are more higher in energy than if they're separated within the same suborbital. Therefore, they spread out as much as possible. All right, we'll go to, let's say, a little bit more room. All right, let's go with the oxygen atom. Now we're talking 8 total electrons, 6 valence, 1, 2, 3, 4, 5, 6, 8 protons in the center. We got the first energy level right here with 2 of them. We got the next energy level right here, 1, 2, 3, 4, 5, 6, 1s2, 2s2, 2p4. And of course, at this point, my orbital diagrams are starting to fall along with each other. 1, 2, 1, 2, 1, and eventually now we're full. We got to back up and add 1 more. All right, and then we have ourselves fluorine. Fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Missing 1 spot there. So we have 9 protons. We have, at this point, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's your missing location. 1s2, 2s2, 2p5. missing one spot right here. And then we have neon. Neon has a full outer shell, and therefore we might note it looks like that. Alright, so we have 10 protons, and the Bohr model starts to get a little more cluttered here. 1, 2, like so. And then at that point, my electron configuration is 1s2, 2s2, 2p6, and it is full. So a few things you might want to point out about all of these models, and a few, maybe you might say, objectives we might want to have here is you must understand the orbitals and the number of electrons that fit. So you gotta know the fact that we have, for example, on the Aufbau chart here, we got the first energy level holds 2 electrons, the second energy level holds 8, then we have S2, P6, D10 for 18. Knowing the number of electrons and knowing as they fill in, do we have a full shell or do we not have a full shell? Okay, and then we also want to note that a full shell tends to be more stable energy-wise. So at that point, how do atoms get to a full shell? And that leads it more and more into bonding. Okay. Now we'll just sort of walk around here and note that in this case, neon is a very stable configuration, very low energy. So for fluorine to get to this point, it would simply gain 1 electron to become F-1. This guy now has a total of 9 protons, but it has 10 electrons. So it has the same exact configuration as does this guy. So this is the configuration for neon, but it's also the configuration for F-1, which is fluoride. For this guy to become stable oxygen, it would need to become O-2. Alright, so that means it would have 8 protons and, again, 10 electrons. Another version of this. Rolling up a little bit here, we get to nitrogen, missing 3 spots here for its full shell. So it will gain 3 electrons, forming nitride. Nitride, the ide suffix is used a lot. I usually describe it as meaning the negative version of an atom ion. So with its most common source or form. So in this case, again, nitrogen has 7 protons and still 10 electrons. So this, once again, has the same electron configuration as N-3. Neon, fluoride, oxide, nitride all have the same stable electron configuration. Carbon is sort of a little unique in the sense that it's sort of in the middle. It could gain in this direction. So everything so far discussed has been gaining. Another name for gaining is reduction. Or it could possibly lose electrons to expose this full inner shell. Turns out that we would expect, a positive 4 or maybe a negative 4 charge forming if this did happen. Well, for carbon to lose 4 of its 6 electrons or gain 4 and nearly double its electrons is quite difficult energy-wise. But if you were to look at the periodic table, you'd find other elements in its family, let's say, for example, tin and lead, Pb, which are on the same family, germanium, we got silicon and carbon. This whole family, these guys in nature exist as +4 and +4. So these do exist, but in this case much bigger atoms with much more charges, so the change isn't nearly as devastating proportionally. Alright, so now we're at the situation where losing the electrons might be easier to expose an inner shell that might be more similar to helium being full than, let's say, going all the way back to neon. So losing 3 electrons would form Be boron plus 3. Not as common for boron particularly, but right below it is aluminum, which is quite common. In this case, boron or aluminum, let's go with boron. Boron's going to have 5 protons, and it's only going to have 2 electrons, same as this guy. So this is helium and Be plus 3, boron plus 3. And then we got beryllium, again losing these 2 electrons to expose its full inner shell, Be plus 2. Same as helium, Be plus 2, and lithium, of course, losing 1 electron, would be lithium plus 1, and the same configuration here. So all of these guys are now what we call isoelectric. Isoelectric is, I guess, a common term. Iso meaning same electrons, same electron configuration, same number of electrons. So a quick summary here, okay. We have full shells here and gaining and losing electrons. Let's draw a little picture of a periodic table here. Things you should know at this point. One valence electron, 2 valence electron. These are the number of valence electrons. Okay, and then their most common charge the family takes on based on acquiring a full shell would be plus 1, plus 2, plus 3, plus or minus 4, and this is the tipping point, minus 3, minus 2, minus 1, and nothing. Other than that, we've talked about a bunch of stuff here today relative to atomic and electronic models. Showing several different ways which we would model an atom and looking at how electrons distribute around it and so forth. So lots of good stuff here. Thank you very much.